we're going to talk about the logistic equation. To this end, let's recap a few ideas, starting with absolute values. Recall that the absolute value given an ordered field F is defined as follows. Given a number x, we'll say that its absolute value is 0 if x is 0, its absolute value is x if x is positive, and its absolute value is negative x if x is negative. With this definition, we found a few properties. First, the absolute value is always greater than or equal to 0, where the absolute value is equal to 0 if and only if x is 0. Second, the absolute value is multiplicative. That means that the absolute value of a product is the product of the absolute values. And third, we have the triangle inequality. That is, the absolute value of a sum is less than or equal to the sum of the absolute values. We then had a few properties about upper bounds and lower bounds. Say that F now is a complete ordered field, and let A and B be non-empty subsets. Let's assume for the moment that A has an upper bound. Then we know that A has the least upper bound that we call the supremum. For each positive epsilon, there exists an element A sub epsilon such that A sub epsilon plus epsilon is greater than this least upper bound. In other words, we can find an element A sub epsilon that is as close to the supremum as we'd like for it to be. There's a similar statement for the infimum, that is the greatest lower bound. For each positive element epsilon, there exists an element B sub epsilon in our set capital B, such that B sub epsilon minus epsilon is less than the infimum of capital B. Just like before, we can find an element B sub epsilon that is as close to the greatest lower bound, the infimum of capital B, as we'd like for it to be. We now remind you of a few properties about least upper bounds and bounded sets. Let's say that F is now an ordered field, and let capital A be a subset of F. Recall that an element lowercase a is an upper bound for the set capital A if A is less than or equal to x for all x in the set capital A. We'll say that an element lowercase b is an upper bound for capital A if B is greater than or equal to x for all x in the set A. We'll say that our set A is a bounded set if it has both an upper bound and a lower bound. Finally, say that we have a sequence of elements x sub 0, x sub 1, and so forth from our ordered field F. We'll say that this sequence is bounded if the set containing them is a bounded set. Finally, recall that a set is bounded if and only if we can find an element capital M such that the absolute value of x is less than or equal to m for all x in our set A. Last time, we discussed a few properties about complete ordered fields, all related to what we call the Archimedean property. Let's let our script f now denote a complete ordered field. For any element x in our complete ordered field, there exists an integer n such that n is less than or equal to x is less than n plus 1. Intuitively, we'll think of this integer n as the floor of x, that is, the greatest integer less than or equal to x. Given any two elements x and y, where x is less than y, there exist integers m and n such that m times x is less than n plus 1 is less than m times y. Finally, between any two numbers in our complete ordered field F, there exists a rational number. We discussed the following question. We've seen that these Archimedean properties hold if we have a complete ordered field. But what if our ordered fields are not complete? We found an example of a field which is not complete, yet the Archimedean property holds. And we found a field which is not complete where the Archimedean property fails. For today, I'd like to discuss a motivating example before we jump into some definitions. Let's consider the following example of a sequence in order to gain some intuition. Say that we have a loan for $10,000. It accrues interest at an annual percentage rate of 12% compounded monthly. How much will we have to pay per month if we wish to pay off the loan in 4 years? In order to answer this question, let's set up some notation first. We'll denote n as the number of months after the loan is acquired. X sub n is the amount of the loan after n months. Rho is the factor by which the loan amount increases, and b will be the amount we'll pay each month. We can put all of this together with the specific numbers in the motivating question to try to find out what's happening with some of these variables. Since x sub n is the amount of the loan after n months, we see that initially, when n is equal to 0, we have a loan of $10,000. This means x sub 0 is 10,000. We then have an annual percentage rate, which means that the amount of the loan will increase based on this interest. We see that we have 12% annual percentage rate compounded monthly. That means that we'll take our 12% and divide it by 12 months. So this rho here is now the factor by which the loan amount increases. So it should be 1 plus 12% divided by 12 months, which comes out to the factor of 1.01. Now we can see that our loan amount will increase in the following way. If our loan amount at month n is x sub n, then we'll have to increase by a factor of rho, but then we'll pay off an amount b, which means that the amount we have for the next month, xn plus 1, is rho times xn, this is the factor by which it increases, times the amount at month n, plus b. Of course, our b will be a negative number since we are paying off each month. Since there are 48 months in 4 years, we'll want to have x sub n equals to 0 when n equals 48. This is where we'll pay off the loan in 4 years. The idea is that we'll have to solve for b. To do so, let's first come up with a closed formula for our amount x sub n. In general, say that we have a sequence x0, x1, and so forth, defined recursively by xn plus 1 is rho times xn plus b. Then we have the following closed form formula that you see here on your screen. We're going to prove this by induction. So let's consider the following proposition as a function of n, which is simply the formula that you see above. To consider the base case, we'll set n is equal to 0. But this is rather easy because then we see x sub 0 is equal to x sub 0. So instead, let's consider n is equal to 1. By staring here at the screen, we see that in either case, we find x sub 1 is rho times x0 plus b. But this, of course, is exactly the recursive relation. So the base case is true. We can now state our inductive hypothesis, assuming that this statement p sub n is true for some integer m. Let's consider now our inductive step. So what happens when n is m plus 1? Using our recursive formula, we now see that x sub n we can express in terms of x rho xm plus b, and we'll simply use our inductive hypothesis. In the case where rho does not equal to 1, we simply do a little bit of algebra and we find exactly the formula that we expect. In the case where rho does equal to 1, again, we do a little bit of algebra and we find exactly what we expect. So this means that our statement p of n is indeed true for all natural numbers n. Now that we have a closed formula, we can answer the question at hand. As a reminder, we have an initial loan of $10,000 that accrues an annual interest at an annual percentage rate of 12% compounded monthly. We wish to pay off the loan in 4 years. As stated above, we want x sub n equals 0 when n is 48. we know that x0 is 10,000 and rho is 1.01. So plugging in the formula above, we can then solve for b to see that it is negative 263.338. Rounding everything to the penny, we see that we must pay at least $263.34 each month in order to pay off the loan in 4 years. But let's make a few observations about these ideas. In general, we had a set A, which consists of these real numbers, x0, x1, and so forth, in terms of the sequence defined recursively by xn plus 1 equals rho times xn plus b. We can find a closed form formula by looking at this recursive sequence. Now, looking at the formula, we can make a few statements about what happens to the behavior of our sequence x sub n. Let's say for the moment that rho is greater than 1. Then we'll see that our rho n gets arbitrarily large so that the terms x sub n grow without bound. Sometimes we'll write the statement x sub n tends to infinity. Either way, we'll see that our set A is not a bounded set. Indeed, the terms grow without bound. On the other hand, let's say that our rho is between 0 and 1. Then rho to the n gets arbitrarily small so that the terms x sub n approximately behave like b divided by 1 minus rho. Either way, the x sub n's are a bounded set of numbers. So our set A is a bounded set. That is, we have a bounded sequence. We're going to try to generalize this by maybe looking at some numbers to get an idea of how this might work in other cases. Let's now look at a slightly different type of recursive relation. Here we see xn plus 1 is rho times xn times another factor, 1 minus xn. This is called the logistic equation. Here are a couple of motivating questions. Can we predict whether the set A is a bounded set? Can we predict the behavior of xn as n increases without bound? To get some ideas, let's compute various tables as we fix x0 equal to 1/3, but we'll vary this parameter rho. First, let's consider some examples where rho is between 1 and 3. In the case where rho is equal to 1, you can see that the terms get smaller and smaller, so eventually xn tends to 0. When rho is equal to 2, again the terms get smaller and smaller, but they don't tend to 0, they tend to a finite number, in this case 1/2. When rho is equal to 3, again the terms get smaller, but they actually tend to 2/3 rather quickly. Let's increase our rho slightly. Now it's greater than 3, but less than or equal to 1 plus the square root of 6. Again, we start with x0 is equal to 1/3, and we start to compute various numbers. We can see here that after the first 10 terms or so, we can't really see a pattern. It seems to maybe go up to 0.69, then jump down to 0.65, but it's very difficult to see exactly what's happening. Something similar happens when rho increases slightly to 3.2. Again, there doesn't seem to be a pattern here if you look at the first 10 numbers in the sequence. By increasing even more to rho is equal to 3.3, again, we really don't see a pattern. Instead, let's move out further in the sequences to see if we can get a better idea of what's happening. We'll start at the same idea of rho is equal to 3.1, but now let's see what happens if we look further out in the sequence. Now a pattern emerges. We'll see that we're bouncing back and forth between 0.56 and 0.76. The numbers are bouncing back and forth between two different values. Similarly, when rho is equal to 3.2, we see that the numbers in our sequence are bouncing back and forth between two different values, namely 0.513 and 0.799. The same thing happens when rho is 3.3. our values seem to be bouncing back and forth between two different quantities, 0.479 and 0.823. Let's give some general remarks about what we've seen with the numbers here. If rho is between 1 and 3, then we've seen that our sequence seems to tend to just one value. It turns out that it's the quantity rho minus 1 divided by rho. However, if we increase rho slightly, just a little bit greater than 3, we'll see that our sequence oscillates between two limiting values. Here's an explicit formula that you see here on your screen. The plus or minus square root denotes the two different values that we've seen before. Actually, something strange happens if you increase rho even more. In this case, rho is equal to 4. There's actually chaotic behavior. We're going to come back to this example later on in the course and discuss what's really happening here and actually try to prove some of the statements that we've seen. Thanks for watching.